We'd like to continue the discussions of common gate amplifier, and we have just derived in class that the current gain is equal to -1. So it's a unity gain. Whatever comes into the source will go out from the drain. The other important circuit parameters for the two-pole model is input resistance and output resistance. So this will be a good opportunity for us to practice the input resistance calculation. So again, let's look at the common gate amplifier. So let me start with the entire amplifier, and starting with the VT here. So this will be a test voltage, okay? And this is RD. So transforming this to AC equivalent circuit, we have a gate that's grounded. We have a source. The source is now connected to a test source, VT, and with a current IT. And here is the transconductance, GM, VGS, and here is VGS, and R0, okay. And we also have RD and RL. So RD goes all the way to the ground, okay. And we also have RL, which we need to include, and we can actually combine RD and RL and call these two resistor R prime, which is equal to RD in parallel with RL. And next is just to do small signal KCL, KVL, and relate all the parameters in terms of IT and VT. So we can start with KCL at source. So we apply Kirchhoff current law at source terminal. Okay, so IT is the current that goes into the terminal, and the current GM VGS is also the current comes into the terminal, and the current flowing out of the terminal will be VS, actually will be VT. VT, that's the terminal at the source, minus V out, VO here, minus VO, and divided by R0. Okay, this is R0 here. And next, we just relate all the items that are related to VGS. Okay, so VGS is equal to 0 minus the source voltage is VT, so it's simply minus VT. What about V out? V out is equal to minus the total current that will go through the R prime, the parallel combination of RD and RL. And as in the previous derivation for the current gain, all the current that flows through the entire dotted circle here must also flow out of this circle. So the current that goes through both RD and RL is simply equal to IT. So it's simply equal to IT times R prime. Okay, so substituting this back into the KCL, we have IT, let me write it better, IT minus GM VT, and this is equal to VT divided by R0 minus V out, which is IT times R prime and times 1 over R0. Okay. So rearranging the terms, we'll have IT and 1 plus R prime divided by R0. This is equal to 1 over, this is equal to GM plus 1 over R0 VT. So we are now ready to express Rin. Rin is equal to VT divided by IT, which is equal to, here is GM plus 1 over R0, and in the numerator is 1 plus R prime R0. Okay, so looks complicated, but we can look at typical values. Typical values for these circuit parameters. Well, GM generally is on the order of many Siemens. So let's say typically it's a 0.5 millisiemens. Siemens is the inverse of ohm. R0 is on the order of say 200 kilo ohm. Okay, just a typical value. Let me change this to on the order of, okay. And so generally R0 is considered a large resistance. R prime, which is equal to RD in parallel with RL, and RD through DC bias, we say, well, it's kind of in the kilo ohm range, okay. So RL, we don't know what RL is, but assuming RD is the smaller of the two, then this will be kind of roughly equal to RD. So R prime is in general much, much smaller than R0, which says we can basically drop this term from the numerator. Now, comparing GM and 1 over R0, 1 over R0 will be a small number since R0 is a big number. This will be equal to 0.0, or I'll just simply say 1 over 2 times 10 to the 5th. So it's about 5 microsiemens. So 1 over R0 is much smaller than GM. So we can also drop this term. So Rin is basically approximately equal to 1 over GM, okay? So we have solved the input resistance using the standard process that we have practiced. More importantly, 1 over GM is a small resistance. So this is one way to get a small input resistance, okay? So anytime we have current drive, current source, we like to have a small input resistance. Well, this is one of such circuit element. Compare with the common source we just solved earlier. The input resistance is infinity. So this definitely offers much smaller input resistance. Okay. Next, turn our attention to the output resistance, R out. So R out will be applying basically a similar rule. So let's redraw the circuit here. Let me redraw the entire circuit here, actually. So this is ground, and this is AC grounded also. And this has RL. Now, instead of RL, we'll be applying a test voltage, VT, and we'll try to calculate IT. And in places of source, we will open the source, current source, and replace it with source resistance, RS. So we will include the influence of the source resistance when we look from the output. So next is to replace this with a small signal equivalent circuit. The gate again is grounded. The source is not grounded. It's connected to ground by RS. And here is VGS, okay? And we have GM, VGS, dependent current source. We have R0, okay? And now to simplify the circuit, I will first find the output circuit of the lower half of the circuit, okay? And whatever I find, the equivalent circuit of this lower half, I can simply add the top part by putting them in parallel. So I'll find Rout prime first, which is simply the equivalent output resistance looking down, okay? So if I do this simplification, then attaching to the drain will only be my test voltage source, VT, okay? And I'll be calculating IT here, all right? So again, we will be applying KCL. So I'll apply KCL at drain, okay? At drain. Okay, so this says IT, the current going in, is equal to current going out, GM VGS, plus the current going through R0. So this path of the current is VT minus, well, we don't know the voltage here. So let's call the voltage at source VS, okay? So VT minus VS and divided by RS, okay? As in before, we will write the individual component. VGS is equal to 0 minus VS, so simply minus VS. And VS itself is equal to, again, if I draw a circle here, the entire circle covered by the green line here, okay, all the current going into this green boundary will be equal to the current going out. There's only one pass in and there's only one pass out. The gate is open circuit. There's no circuit, no current going to the gate. So VS is simply equal to IT times RS, okay? So substituting these two into the KCL equation, and we will have IT equal to GM minus VS. So I'll put a minus sign here. VS is IT times RS, all right? And plus VT divided by RS and minus VS, okay, minus IT times RS. So VS here. So here is IT, okay. Let me erase this part. So this is VT minus VS minus IT RS and divided by RS. Okay. Yes, I think this is correct. So basically, we just substitute these equations. So IT And this term 1 plus we move this term over to the left-hand side. So this will be GM RS, okay? And sorry, I think there was a typo here. It doesn't feel quite right. The RS here should be R0. This is the current that goes through this path. So let me correct that also. This should be R0. Okay, now this is correct. So there's one more IT term. This term, we'll move it over to left-hand side. So plus RS divided by R0. Here is RS also. And this is equal to the only term left on the left-hand side, VT over R0, okay? So R out will be equal to VT divided by IT, and this is equal to multiply R0 to the left-hand side. This will be equal to R0 plus GM RS R0 plus RS. So this is a very interesting results. So we ended up having 3 terms here. And again, let's use the typical value to gain more insight into this. So R0 is on the order of 200 kilo ohm. So it's a large resistance. GM, let's say 1/2 millisiemens, okay? RS is on the order of a few kilo ohms, right? And well, this is actually unknown. We don't know what the source resistance is. So let's leave it there. So from these 2 numbers, we know GM R0, which if you recall, this is the intrinsic gain of the transistor in a common source configuration. So this is a large number. This number is on the order of 100, multiplying these 2 numbers. So GMR0 is certainly much greater than 1, okay? Which means the second term, which is GMR0 multiplied by RS, is definitely much greater than RS. So we can safely drop this term independent of the value of RS. So with that simplification, R out is equal to R0 plus GM R0 times RS. So this is most likely a resistance that's much larger than R0. So this gives you a very large output resistance, okay? So if you recall, for current amplifiers, it is desirable to have a very large output resistance. So we can complete the 2-port model, okay, for common gate amplifier, CG. So we will write it as R in here, okay? This is R in, okay? And we have a dependent current source, okay? And the current source is really -1 times I in. So here is I in, -1 times I in, okay? And this is a current amplifier. We have R out here, okay, R out. And this is the output port, okay? So this is the 2-port model, and R in, we just derived, is 1 over GM. So we said we should have this as small as possible. So it is indeed a small input resistance. R out, we just derived here. It is R0 plus GM R0 times RS. So this is indeed very large. So this is a good configuration for a current amplifier. We did not amplify the current, but we provide a very useful impedance transformation. We present a low input resistance to the source, and we present a very large output resistance to the load. So even though the current has a unity gain, we have provided the very important transformation. Let's come back to this picture here that we just said. Well, we only take the output resistance of the bottom half. The upper half is RD. So strictly speaking, this what we have calculated is actually RR prime. Okay, this is actually RR prime here. So the real R out. So here is RR prime also. The real R out is RR prime in parallel with RD. So this is equal to RD in parallel with R0 plus GM R0 RS, okay? And if we continue our argument for the typical value, we say, well, RD is usually on the order of a few kilo ohm. So it is already much smaller than R0. So a likely outcome of this is R out is now approximately equal to RD. Well, this drastically reduces the magnitude of the output resistance, which is not desirable. And it will be much more desirable to have RD not degrading the output resistance. So this is possible with alternative biasing schemes. So again, if we use current source to bias a common gate configuration. So this is the ground, and this will be our input, and this will be our output. Okay, and in this case, we will similarly obtain an RL prime, which is equal to just what we observed before. But if we look up to the current source, this R is basically infinity. So if we use this biasing scheme rather than RD, then our R out will remain very large. This is R out prime in parallel with a resistance that's infinity. So this is still R out prime, which is R0 plus GM R0 times RS. So this will preserve the large output resistance, which is desirable for current amplifier. Okay, so that's very interesting. We have obtained an alternative type of amplifier configuration that provides current amplification with low input resistance, high output resistance. Okay. Very often, as we go on, actually, we will also use a common gate as voltage amplifier as well. Okay, and we can analyze what would be the gain if we use this as a voltage amplifier. And actually, this problem become very simple. We have already done the hard work of figuring out the two-port model. So we can basically just take the two-port model of a common gate. So it is input and R in is 1 over GM, all right? and we have current gain -1 of I in, and I in is the current coming into the input terminal, okay? And we have R out here, right? And if we are using this as a voltage amplifier, we'll be measuring V out here. And we will be connecting voltage source. If we ignore the source resistance, we will have basically Vs here, source resistance here, source voltage here. So the input voltage is equal to Vs, and now we'll figure out what is the output resistance. Output resistance, V out here, VO, is equal to the current, basically the whole current, -1 times I in, okay? And this current is going upward as indicated by the arrow in the drawing in the dependent current source, okay? So it's going upwards here, which warrant another minus sign in front to be equal to and times R out. So this will be equal to V out. And what is I in? I in this case, is simply Vs, the input voltage, divided by the resistance, which is 1/Gm, okay? And so this simply equal to Gm times Vs. So combine these two equations, we'll say, well, V out, well, let's go one step further for the first equation. So VO is equal to, the 2 minus sign cancels out, simply equal to I in times R out, and we substitute I in here. So this is simply equal to Gm Vs times R out, okay? So the voltage gain, AV, is equal to VO divided by Vs, okay? And this is simply equal to Gm R out, okay? Now it's interesting to compare this with the output, with the voltage gain of common source amplifier. It has a similar form. So recall that for common source amplifier, okay, AV is equal to Gm times R out. R out is R0 in parallel with RD. Now, if we use a current source, this goes to infinity if we use a current source biasing. Okay, so this fundamental gain will be, actually there's a minus sign here. So there's a minus sign here. So minus Gm R0. So you see there's quite a bit of similarities in these two voltage gains. It's Gm times R out. But the R out in common gate is much larger than R0. So because R out here, is equal to R0 plus Gm R0 times Rs. So usually this end up to be much greater than R0. So we are able to obtain higher gain, actually, higher gain in common gate amplifiers, okay, compare with common source amplifier. However, we need to consider the input-output resistance in the entire circuit amplification. But this gives us a hint that potentially common gate amplifier, even though it's a unity gain current amplifier, it can be used to boost up the gain of a voltage amplifier. Okay, but using this simply as a voltage amplifier is not so desirable. Uh, First of all, the input resistance is too small. Output resistance is too large. So we need to combine these in some manner to obtain the optimum high voltage gain. This will be the subject of multi-stage amplifier, which we will discuss later. Okay, I'll stop here and we'll continue with a review of the topics and materials on Thursday's class.